right?
Oh yeah,
Yeah.
very well.
Did you talk like that?
9.
Alright, I think people are still out and about, but we're gonna go ahead and get started. If I can. I know your brains are either really full still or really empty. One way or another, it's probably not optimal learning right after you've taken a practical, but we are just doing a review today. And what I've done is kind of gone through and thought about the things that you need to study and picked a few of those things to actually review in detail. Obviously, don't let this be the only studying that you do for the final. This is to help you prepare, more or less. So I'm happy to answer questions as we go through as well. So we'll go ahead and get started. Starting sort of from the beginning of the semester, week 1, you had to identify brain structures, and we built from week 1 and added more brain structures as we went. But you do need to know the basic function of the areas of the brain that we discussed in this course. So for example, like this could be a matching question where there are a variety of structures listed, functions listed on the other side, and you have to match the function with the structure. So we talked about, and there's actually 5 lobes if you count the insular lobe, basal ganglia structures, limbic structures, the cerebellum, thalamus, hypothalamus, midbrain structures, including things like the red nucleus, the colliculi, the periaqueductal gray, the reticular formation. And then we talked about some specific cortical regions, things like frontal eye field, premotor, and SMA areas. So this is sort of a hit list of ones that you should definitely make sure that you can identify the primary function of those cortical areas. You still need to know cranial nerves. I'm not going to ask about any one of these in any specific detail, but you know, oculomotor nerve or oculomotor nucleus came up a lot when we were talking about brainstem strokes. So you still need to be able to think about, well, what do I lose? What happens if I lose my oculomotor nerve, my oculomotor nucleus? What happens if I have corticobulbar palsy and lose functioning of like the tongue and the areas around the mouth? What does that look like? So you don't need to go back through and memorize all of the specifics of these, but at least again, familiarity with function would be appropriate. In terms of studying sensory systems, the way we went through, particularly the sensory pathways, was looking first at receptors. What types of receptors are there for the somatosensory system, for the auditory system, for the vestibular system? What activates those receptors? Is it pressure? Is it movement? Is it a chemical in the environment? So be able to identify where the receptors are, so location of receptors, and how those receptors are activated. Think about the major projections pre-thalamus. So you're thinking about, we'll go through the DCML, but DCML, dorsal, or the cell body is located in the dorsal root ganglion. It's going to travel in the cuneate fasciculus. It's going to synapse on the cuneate nucleus. Like those are all sort of landmarks along the way in that pathway. If you're thinking about auditory or vestibular system, think about the ganglion outside of those systems. Can you name those? So big picture sorts of things. Think about laterality. Where do those pathways cross? That's going to be important for when we do lesions. You need to know if that pathway crosses in the medulla or the midbrain, because the manifestation is going to look different. The sensory loss is going to be different based on where that stroke occurs and whether that pathway is crossed or not. Think about for each of the sensory systems what thalamic nucleus they project to. That would be another matching sort of thing that I could throw at you. I could list a bunch of thalamic nuclei, and then on the other side, sensory systems or motor systems that project to those specific nuclei or functions of those nuclei. And then with sensory pathways from the thalamus, how do they get to the cortex? to know where they end up. And again, the functions of each of these pathways, which is usually pretty self-explanatory, interpretation of deep pressure or pressure touch or proprioception or sound. But thinking about what a lesion in that pathway would look like, what loss would you have if you lost that pathway? So these are all the sensory pathways that we did. There is a lot of them. I tried to specify which ones that you really just need to know the function of, or kind of the general structures like the start and the end point. I would say if I had to make a priority, these would be the 5 that I would prioritize in terms of knowing in detail. Those are the DCML, the dorsospinocerebellar, mainly because we talked about that related to the cerebellum, so that came up in both halves of the semester. So anything that we hit on in both semesters is probably going to be weighted with a little more importance. Spinothalamic tract, ventral trigeminal thalamic tract, which carries most of that touch and somatosensory information from the face region, and then retinofugal projections, just meaning that input coming in from the retina going back to the primary visual cortex. So I'm going to go through a couple of these with you. I'll go through DCML, spinothalamic, and retinofugal. So just as a reminder, DCML stands for dorsal column medial lemniscal tract. So when it's running through the cuneate and gracile fasciculus, it is the dorsal columns. When it's running through the brainstem, we're mainly talking about it as the medial lemniscal tract, which was on your test, medial lemniscus. Anybody put that? Okay, good. So the function or the purpose of this tract is discriminative touch and proprioception, the 2 major functions. Receptors are located in skin, muscles, and joints. Some examples are Meissner's corpuscles, Merkel's discs, muscle spindles, those sorts of things. There are more. Things to remember in terms of the pathway, that cell body is located, of the first order neuron is located in the dorsal loop ganglion. It travels in either the gracile or cuneate fasciculus. So if it's lower extremities, which one is it traveling in? And upper extremities, cuneate. It's going to synapse on that second order neuron in either the gracile or the cuneate nucleus. Will decussate at the level of the medulla. Then from there, going to the VPL, the ventral posterior lateral nucleus of the thalamus, and then it will travel in the internal capsule to S1. So this would be an example of the level of detail that I would want for the DCML tract. And then again, if you go back to your old lectures, well, most of them with pathways have videos. I'm not going to re-show the videos today, but if it helps you to see it visualized, then you have those to refer to. Spinothalamic pathway. First order neuron, we have those receptors in the periphery. They will travel into the spinal cord. Before they synapse, what's going to happen? Travel up or down in what? The Sowers fasciculus, and then they'll synapse in the dorsal horn where? Substantia gelatinosa, right. And then what happens? After the synapses on that second order neuron cell body in the spinal cord, what does it do? It crosses in the anterior white commissure, and then it's going to travel as the spinothalamic tract in which system? The anterior lateral system, right. Then it's going to go to the thalamus. It's also going to synapse in the VPL of the thalamus, just like the DCML tract. And from there, just like the DCML, it's going to travel in the internal capsule to the primary sensory cortex, primary somatosensory cortex. And again, this pathway is carrying pain, temperature, and crude touch. Mainly talk about it as pain. Just a reminder that those sensory systems, from the point of the receptor, as they travel into the central nervous system, are going to be carried along axons of different levels of myelination. The more myelinated they delta or C fibers. C fibers being unmyelinated, so much slower. Type 1 or A alpha fibers are usually going to be coming from muscle spindles or GTOs, so they're carrying what type of information? Proprioception and usually unconscious proprioception, right? And then I feel like you guys knew vision really well. You did well on that on the exam, but just a reminder of those retinofugal pathways. We have information coming in. Each eye is picking up information from the left and right visual field. From the right visual field, it's going to project onto the left temporal retina and the right basal retina, the opposite for the left visual field. Information travels down the optic nerve. The retinal fibers will cross at the optic chiasm. The temporal fibers do not cross, so it ends up that all of the information from the right visual field is traveling in the left visual tract, or optic tract, and all of the information from the left visual field is traveling in the right optic tract. Synapses in the LGN of the thalamus, another thalamic nuclei that you should be familiar with. From the LGN, fibers travel as optic radiations back to the primary visual cortex, which is also on your lab exam. As a reminder, optic radiations have two branches. One is Meyer's loop, which is in green here. Sorry, that box keeps popping up. Meyer's loop travels in the temporal lobe and carries information from the superior quadrant. So if you're having a disorder of superior quadrant synopia, then you're talking about a lesion just to the Meyer's loop portion of the optic radiations. There's also this medial superior branch that carries information from the inferior visual field, and that's traveling in a part of the parietal lobe. So when we think about temporal lobe or parietal lobe strokes, you may see a manifestation of visual deficit that is not just pure hemi-neglect, but rather a loss of a quadrant in that specific side of the visual field. You guys good on visual stuff? It's all coming back to you now? Okay. In terms of motor, that's where we went to next. And we sort of did some general principles of motor functioning. We talked about the difference between upper and lower motor neurons. Where do we find these neurons in the brain? So if I ask, where do we find the cell bodies of lower motor neurons, what would you answer? Not dorsal root gate. No, nothing dorsal. Motor, we just shifted. Sensory to motor. Where is motor located? In the spinal cord. Ventral horn of the spinal cord. So lower motor neuron cell bodies are going to be in the ventral horn of the spinal cord. It will go out to the periphery and synapse on extrafusal muscle fibers. There's whispering. Was that confusing?
Is that the same thing?
I don't know what's
The sensory is posterior and anterior.
Sure, I didn't teach you. I've never heard that before, but
Okay.
sensory is coming in dorsal, motor is going out ventral. Yeah.
So now we're whispering about the exam.
Oh.
That question, what type of motor neurons? What type of neurons?
Yeah, those would be efferent motor neurons
What if
or
we
lower
put
motor
ventral
neurons.
rootlets?
That's not what I asked.
I think that.
She'll argue later.
Consider that one of the bonus ones. Okay, so upper motor neurons, lower motor neurons, know the difference between the two, where they're located. Also know the difference between upper and lower motor neuron disorders. We spent a fair bit of time talking about how you distinguish between upper and lower motor neuron disorders, to make sure that you know the features of each, but be able to distinguish between the two of them. Some other other things, just terminology. Know what a motor unit is, what the difference is between a motor unit and a motor neuron pool, the difference between alpha versus gamma motor neurons and what they synapse on. How is that different? Talking about intrafusal versus extrafusal muscle, and this alpha versus gamma plays into intrafusal versus extrafusal, and know what the concept of reciprocal inhibition is, and where we might see that. And then we did 3 spinal reflexes, the stretch reflex, the flexor withdrawal reflex, and cross extension reflex. I'm probably not going to ask you to draw those out, but you should be familiar with what they do and how many synapses are in each of them. So just a reminder, when we talk about motor units, there are 3 types: slow oxidative, intermediate or fast oxidative, and then fast glycolic. And again, I would be familiar with sort of the function of each of these, and also how they're activated. So what is one way, or what's one principle in terms of how these types of motor units are activated? I'm not asking that well. What order are these activated in? Okay, so they're activated slow to fast. So one of the principles in how they're activated is order. That no matter what the action, even if you are sprinting, your body's going to go through a process of first activating the slow, then the intermediate, and then the fast glycolic. We are able to, even though most muscles have about a 50-50 distribution of slow to fast, or fast oxidative or fast glycolic, we are able to change that somewhat. So that if you're distance training and doing a lot of cross-country type running, your fast glycolic can change over to fast oxidative. Similarly, if you are doing a lot of weightlifting or speed training, there is some change that can happen in the other direction. So the metabolism of the muscle fibers can change. Wanted to run through alpha-gamma coactivation. Again, I picked out ones that I thought maybe have possibly slipped your mind, so I apologize if you remember all of these in detail. Extrafusal muscle fiber is innervated by alpha motor neurons. So that's the green fiber coming in, synapsing on the extrafusal muscle fiber here. This is a muscle spindle in yellow. The fibers of the intrafusal muscle fiber of the muscle spindle are innervated by gamma motor neurons. So gamma motor neurons are innervating intrafusal fibers, alpha motor neurons, extrafusal muscle fibers. The orange is the 1A axon, so the sensory. Yeah, go ahead, Zach. All right, yeah. Why don't I get through this and then you can ask, okay? Okay. The orange one is the 1A axon, so that's the sensory afferent. What type of information is this carrying if it's coming from the muscle spindle? Information about what? I'm hearing all of your answers and I'm not hearing what I want to hear. What does the muscle spindle provide information about? Length, muscle length. Muscle spindle provides information about muscle length. Primarily muscle length. So, in this state, we have an active 1A axon that is sending information about the length of the muscle. If there was a situation where that alpha motor neuron became active and the extrafusal muscle contracted, there is potential then that the muscle spindle would become slack. If the muscle spindle became slack, the 1A axon would not be able to fire. Okay? So this is a hypothetical. If we only had activation of the alpha motor neuron and contraction of the extrafusal muscle fiber, the muscle spindle would become slack, and the 1A afferent would not be able to fire. So instead, what happens is alpha gamma coactivation, which is shown in figure C. So the alpha motor neuron fires, the extrafusal muscle contracts, the gamma motor neuron fires, and tightens the ends of the muscle spindle, making them taut, allowing the 1A afferent to continue firing and providing information about muscle length. Yeah.
There's no condition as named where this happens in people.
Where like this would happen and they don't get information? Not that I know of. And this is kind of just one of those things that's pretty well said. Yeah.
The little vertical lines, are those showing what's being activated?
Yes.
So in the last one during the coactivation, why isn't there lines on the brain?
I think they're just saying if it had been activated here, this is what happens to the muscle spindle. So if you want to draw little lines in here, that's fine.
Okay.
But it is co-activation. They're both being activated. You guys good on this?
Yeah.
I'm seeing ponderings. No? Okay. Zach, is this the one you wanted me to go to?
No, it's about the muscle fibers.
Okay.
It was just like curiosity, so just make sure slow or stay slow, but intermediate and fast pace change depending on what you're doing, long distance or.
For the most part, I'm sure there are conditions where slow could change if there was a specific type of training, but mostly what we see is a transition between intermediate and fast oxidative and fast glycolic. Okay, so we went from general motor principles to talking about motor pathways, and I said that as you're studying motor pathways, the important things to think about are where does it start? So where's that cell body located? Where does it course through? What are major synapses or landmarks along the way? Again, with laterality, where does it cross? And that'll make a difference if there is a stroke or a lesion of some sort. Where does it terminate, and what is the function of the pathway? So fewer motor pathways that we learned, so you are responsible for all of these. The one that we probably spent the most time on was the corticospinal tract, so I'll go through that one. So for the corticospinal tract, that first order neuron, the cell body is located primarily in the primary motor cortex, and also the premotor supplemental motor areas. So areas 4 and 6, Brodmann's areas 4 and 6. And really that neuron goes all the way down to synapse on lower motor neurons in the ventral horn of the spinal cord. Sometimes they'll synapse on an interneuron before they synapse on a lower motor neuron. That's less important right now, but the idea is that their target is to activate a lower motor neuron. So the important thing with this tract then is to understand where it courses through. So from the cortex, it's going to travel through the posterior limb of the internal capsule. It'll travel through the cerebral peduncles and that middle 3/5 of the cerebral peduncles. It'll course through the pons and then eventually end up in the medulla running as the pyramids. You saw the external surface of the pyramids on your lab exam, right? Okay. Yes or no? Okay, so at the pyramidal decussation, so the caudal part of the medulla, it's a heart-shaped thing. We have the pyramidal decussation where 90% of the fibers cross to become the lateral corticospinal tract. It was also on your lab exam. And these will terminate contralaterally. Lateral corticospinal tract is carrying information function or will activate what type of musculature? Distal musculature. So mostly going to the upper and lower extremities. So we'll run the full length of the spinal cord. Most of the remaining fibers will run ipsilaterally as the anterior corticospinal tract, crossing once it reaches the level of the spinal cord that it's going to synapse at, and it will synapse bilaterally in most cases. Yes, Hannah?
I was just confused about this earlier, but corticospinal in the chart that's comparing lateral and anterior in our, like in the original notes, it says that lateral only goes to cervical and lumbar.
Primarily goes to cervical
But
and
we should
lumbar.
just know that it goes all the way.
Yeah, the track itself runs the full length of the cord
Okay.
because it has to go all the way down to lumbar vertebrae.
Okay.
And the anterior corticospinal tract is not doing much in terms of distal musculature. What is its primary function?
Posture.
Posture, so it's innervating mostly proximal musculature. And this was just a diagram, again, starting in this example, the primary motor cortex, or M1, traveling ipsilaterally through midbrain, pons, medulla, until it hits the decussation, where most of those fibers are going to cross and run laterally. The rest of them are going to run in the ventromedial group, anterior corticospinal tract, until it reaches the spinal cord level where it's going to synapse, and it will cross over and synapse bilaterally. Okay, good with that one? When we did basal ganglia, we talked, or you should be familiar with what structures are we talking about when we're in the basal ganglia, what structures are involved in the basal ganglia related to movement in particular. The only basal ganglia structure that we talked about that wasn't particularly related to movement was what? Talked about in relation to emotion and reward. That is not a basal ganglia structure. It does do those things, but is not a basal ganglia structure. Nucleus accumbens is a basal ganglia structure that is not involved in movement. Except for, hey, I want that beer, or cigarette, or whatever. Motivation. So you should be familiar with the general functions of the basal ganglia, what it's doing in relation to movement as a whole. I will go through the indirect and direct pathways with you again. Make sure you know what neurotransmitters are involved in the basal ganglia pathways, specifically the role of dopamine, how it's interacting on those D1 and D2 receptors to influence movement. And you should be able to identify basal ganglia disorders, what they look like, and to distinguish them, basal ganglia disorders, from cerebellar disorders. So, reminder that this slide is not one of the pathways. This is just a slide to remind you of what the structures want to do on their own, what their preference is. So, the motor cortex wants to excite the striatum, which is the caudate and the putamen. The caudate and the putamen want to inhibit. Whichever structure they're going to, they want to inhibit. So they function to inhibit both the globus pallidus internus and the globus pallidus externus. In this slide, it shows you that the globus pallidus externus also wants to inhibit structures that it projects to, and in this case, it's the subthalamic nucleus and the GPI. Subthalamic nucleus wants to excite the GPI. And probably the most important is that the GPI wants to inhibit the thalamus. That's kind of the key player in thalamus, which wants to excite the motor cortex. So again, this slide gives you the basics of who wants to do what on any given day. But it's not a pathway. So when I ask what are the structures of the basal ganglia involved in movement, they are all presented here for you on this slide. Then the substantia nigra, which of course is going to release dopamine, that's going to do different things depending on what receptors it binds to. Let's look at, I forgot about these animations, sorry. Okay, so direct pathway. I feel like again you guys do really well in this quiz, so hopefully it's all still in your brain. But again, the cortex wants to excite the striatum, and in this case, nobody's stopping it. The striatum then is free to inhibit the GPI, which is what it wants to do. The GPI, though, wants to inhibit the thalamus. It's an inhibitory structure. When we inhibit an inhibitory structure, we make it less able to do what it wants. So the GPI is less able to inhibit the thalamus, which makes the thalamus free, or leaves the thalamus free to excite the motor cortex, which in the end gives us or facilitates movement. Right? Okay. And in this model, the role of dopamine, it goes along with everything. It doesn't really change anything about the direct pathway. It just facilitates it because dopamine that's released from the substantia nigra pars compacta binds on D1 receptors in the striatum. So it's exciting the striatum, increasing its ability to inhibit the GPI. So in this case, dopamine just helps to facilitate what the direct pathway is already doing. It doesn't change anything. Good with direct pathway? Okay. Indirect pathway, again, this is without the role of dopamine. The cortex excites the striatum. In this case, the striatum is going to inhibit, but it's not inhibiting the GPI, it's inhibiting the GPE. When we turn down activity in the GPE, it's not going to be inhibiting these two structures like it normally would. So we're reducing inhibition to the GPI. And we're also allowing the subthalamic nucleus to excite the GPI. And together, here's my pointer, it allows the GPI to do what it wants to do. Because we're reducing inhibition and we're adding excitation. So we're helping the GPI do what it wants to do, which is to inhibit the thalamus. If the thalamus is inhibited, it can't excite the motor cortex as much, and the net result is a reduction in movement, or a decreased facilitation. So without dopamine in the picture, the indirect pathway reduces movement. Okay? Then the last part is when we add dopamine into the picture. Remember the video that you guys have the link for talks about the sort of being the thalamus having a leash on the cortex. And when dopamine is added into the indirect pathway, it tightens the leash. It loosens the leash. So the indirect pathway is tightening the leash, making the thalamus not as effective. And the role of dopamine in the indirect pathway is to loosen that leash by having dopamine bind on D2 receptors in the striatum, reducing the inhibition of the striatum on the GPE, which frees the GPE up to inhibit the GPI. Also by inhibiting the subthalamic nucleus, we can't excite the GPI. So the net effect here is inhibition of the GPI. It's less active, which makes it less able to inhibit the thalamus, which loosens that leash and allows the thalamus to excite the cortex a little bit more. doesn't fit into this at all. It's just structurally considered part of the basal ganglia.
Why is it important?
It is important when we talk about the limbic system, and we'll go over that in a minute. So if I don't answer it in a few slides, you can ask me. Alright, I would not be surprised if a basal ganglia diagram or a request for you to generate a diagram of one of these pathways showed up on your exam. I haven't written it yet, but it is likely that there will be a question or something where you are asked to do something related to one of these two pathways. Okay, cerebellum. You should know the first few slides on the cerebellar PowerPoint talked about motor and non-motor functions of the cerebellum, so you should be familiar with both. In terms of inputs and outputs, it's a lot of what we did there. You should know what information is coming into the cerebellum, what is going out of the cerebellum, and where, what peduncles that information runs through, and what cerebellar nuclei are involved in those pathways. And this diagram, darn it, I forgot to check all these animations, should be helpful for you, at least in knowing the peduncles and what is running through each one of those. So I would refer back to that one. Back to the slide. In terms of general cerebellar stuff to be familiar with, we talked about 5 important circuits: the cortical cerebellar circuit, the vestibular cerebellar circuit, reticulocerebellar circuit, the circuit between the cerebellum and the red nucleus, and then not a circuit, but the influence of those dorsal spinocerebellar fibers, that dorsospinocerebellar tract, on the cerebellum. Dorsospinocerebellar tract showed up on your lab exam too. And again, you should know what the signs are of cerebellar dysfunction, and being able to distinguish that from basal ganglia disorders. And with cerebellar dysfunction, we talked about ataxia, but we talked about specific aspects of ataxia like dysmetria and dysynergia, those sorts of things. So, be familiar with what those are and how you would test for them. So again, this is going to help you with knowing the ins and outs. And then this is sort of the end diagram that I showed, and I had broken it down on your PowerPoint into what each one of these looks like separately. But this was the end goal, that you understood how the information was coming into the cerebellum, what nucleus it was being processed in, and how and where it was going when it left. So if you understand if you understand this diagram, then you're in good shape. I wouldn't start with this. I would go back and look at the circuits individually before you try and come back to this one. In terms of blood supply, you should know the regions supplied by the anterior, middle, and posterior cerebral arteries, the superior, anterior, inferior, and posterior, inferior cerebellar arteries, and then the other two that we talked about in class were the anterior choroidal and the anterior and posterior spinal arteries. Specifically related to lesions and strokes, you should know what a stroke would look like that results in damage to the anterior, middle, or posterior cerebral arteries. Those are the ones that we talked about the most. Remember, with the posterior cerebral, you may have influence on brainstem, and there were a couple different brainstem strokes that we talked about as well. And then we talked about lacunar strokes, which are usually involving deep branches of these cerebral arteries that affect what two structures? Thalamus and internal capsule. So know what those types of strokes would look like. And as well as cerebellar strokes, which plays into what we talked about related, just what does cerebellar dysfunction look like? If the cerebellum's not working, how is that going to influence the quality of movement? Most likely there will be 2 where's the lesions questions, possibly 3 on the test. Kind of like the practice ones that I gave you and the one that I asked on the quiz. So I would be prepared for, again, 2 to 3 where the lesion questions. Right. So after we did blood supply, we talked about the limbic system, mainly in relation to emotion, but also its associated functions with learning and memory. And I tried to summarize for you here the key structures of the limbic system on this slide and the next one. If we look at just the amygdala, it's mainly going to be important for its role in influencing the hypothalamus, which is obviously important in that physiological response to stressors or emotions. And also it's the primary processor of fear in our brain. It also plays a role in aggressive behaviors as well. The prefrontal cortex we talked about as an important structure integrating emotional and cognitive processes. It's also important in inhibiting the emotional response. So the PFC inhibits the amygdala. At what point in development is this system kind of faulty? Teenagers, right? Their prefrontal cortex is slow to develop. It's not as good at inhibiting the amygdala or inhibiting emotional responses. And then the prefrontal cortex is also important for things like associating the reward value of sensory stimuli. So what is that piece of pizza worth to me? And making decisions about, am I going to eat that pizza or not? What were the 2 parts of the prefrontal cortex that we talked about as most important related to the limbic system? Nope, you're thinking motor planning. Orbitofrontal cortex and medial frontal or ventromedial prefrontal cortex. Remember, orbitofrontal cortex was particularly important when we talked about taste and smell. Direct projections there giving us reward value of those sorts of things. So you have a slide that outlines the specific functions of both of those parts of the prefrontal cortex. Ventromedial prefrontal cortex. And I think on your slide just says medial prefrontal cortex. Other structures in the limbic system that we talked about, nucleus accumbens, which is really structurally part of the basal ganglia, but functionally part of the limbic system. It releases dopamine. What triggers it to release dopamine? Anybody remember? Dopamine from the... Nope, good try though. It does release dopamine. You guys are really close. You're naming all structures that are involved in this. It's the ventral tegmentum. Ventral tegmentum releases dopamine that goes to the nucleus accumbens. Nucleus accumbens releases more dopamine that says, hey, I really, really liked that. So it's involved in pleasure, reward, motivation, and is implicated strongly in addiction, part of the addiction circuit. Other structures that we talked about related to the limbic system, the cingulate gyrus. It doesn't have a unique function, so we didn't outline that specifically. But we know that it's a relay station for all of this emotional stuff. It was in Papez's original circuit that he thought was an emotionally driven circuit. And we know that the anterior cingulate gyrus is strongly implicated in depression. It is overactive in depression. So one of our therapeutic targets for depression is the anterior cingulate gyrus. We didn't say a lot about the medial dorsal nucleus of the thalamus, other than that it was a key relay structure. But again, if I'm listing out thalamic nuclei, medial dorsal nucleus could show up on there. You should know that it's linked to limbic function. And then we talked about the hypothalamus as the key regulator of the physiological responses. And we talked about it that day in relation to the limbic system as being a responder to different emotional events, but it regulates homeostasis and other regular naturally occurring things in the body as well. And then the hippocampus we said is sort of part of the limbic system. It's less important related to emotions, more important to learning and memory. And is involved in the modulation of aggression. So again, this is sort of a hit list for the limbic system. If you don't know anything else about it, I would know what the functions of these different structures are. Sorry. All right, let's stop there and take a break, and then I'll come back, and we don't have that much more to go. We'll do 10 minutes, come back at 5 after.
I'm sorry.
Yeah. You're gonna come and argue with me.
I don't know, I don't want to.
No, it's a correct answer.
Yeah, I think that's where I was confused, because I'm like, in the thing, it's like, it wouldn't ask anything but structure, and so I was like, oh, I'm gonna put the structure, that's not what she's asking, because I did think that's motor, but I didn't put that, because I was like, she's only gonna ask for the structure, so that's why.
Affected by that question. I will make sure that yeah, I'll have to look. I didn't realize it was a different one.
I'm really excited about this.
Some people put what I put, and some people put like what others put in here.
I don't know.
And we're like, you know,
I
technically
kind of
we're
like
both
this movie, but that's why I like the
Yeah, I'll take a look again. And then really not come down. You will get them back.
And it's good.
Yeah, I need to grade them first, then we'll finish grading them. You will have them back hopefully.
No, I've never attached it
So hopefully you will
to that.
grade them.
I understand that.
Yeah. But yeah, so it will get done.
I understand that.
You'll have to get grades back.
Everything else.
Yeah.
That's why I hear people are like, "Well, they didn't do this."
I've had to do that because I really like it.
That's a different problem.
Sarah, you're pretty good at
Yeah.
now.
Like I can see it says about that. Half of it's not the same.
Well, that's even when I look Oh yeah.
Oh, you're up to date. You saw that. Yeah. You know what they're going to do? What's the order? That's tough.
Probably
So we get to see what they're all saying. You know it.
I love how we're cutting off. Good, I'm actually finally I wrote somewhere. Like I wrote
the higher shelf.
I leave my lab guys out and suddenly I only have half a lab guy. Paper on the floor makes his
I live in a world where all of my stuff has to be 6 feet off the
Like
ground.
I had to warn my roommate that if she lets paper out, she like draws. And I was like, if you do something on the floor, he'll make it. So yeah.
The nice thing is that he only does it to get the attention to maybe to feed it. So,
In the middle of the night.
so it's any paper that's in the area around where I can put stuff other places.
Really? So he does it when he's angry. He'll like start in the middle of the night, he'll just start ripping up papers and he knows that it wakes me up. So he'll just sit there and just be like, I'm like,
Usually when he's angry at me, he goes over to me and stuff. Like I'll pick him up and I'll be like messing around with him. When I put him down, he goes over to me. Well, I post his I love it.
Do you all have a second cat in the house?
Hera.
Hera?
Yeah.
Harrah?
No, H-E-R-A.
Oh, like the Greek god. Okay.
We call her Banana.
Wait, whose cat is she?
That's Will's cat.
Oh, okay.
You've never seen. She's been there.
I've never.
You've never seen her before.
Every
because-
time we've been there, she's been there.
Yeah. In the old house, she never came downstairs. Oh, great.